This activity gives you the opportunity to work through the entire workflow for designing a state feedback controller and state estimator for the same system. And remember, one of our key results of doing this combined controller estimation is the fact that you can do these design problems separately, and that separation is one of the fundamental contributions in control theory. So we're going to be revisiting this system, this quadcopter with 2 lost propellers. We've actually already computed the controllability and observability matrices for that. And so I just went ahead. You shouldn't have to compute those by hand. So I'm giving you these matrices, the inverses that you'll need to use in order to create your change of variables to get this system into controllable canonical form and observer canonical form. I'm also giving you some kind of convenience, again, because these are 4x4 matrices, some of the powers of A, so you can do that computation a little bit easier as well. You can do this in MATLAB if you want to, and that's fine. I think that if you're a little shaky with MATLAB or matrix multiplication, it would be a great idea to do a lot of these computations by hand because it's gives you a lot of practice. So what we're going to do is we're going to do pole placement for the controller to have poles at these locations, and we're going to do pole placement for the estimator with poles at these locations. And so I will let you work on this, and if you get stuck, there are many steps to this problem, so feel free to kind of step through and then pause the video as you go through in order to check your solution or to get some hints. All right, so the first step in doing this is to convert to our controller and observer canonical forms. So we're going to tackle the controllable canonical form first. What we do is we build out the rows of our transformation matrix. So we're going to be making this matrix TC, and this TC is going to be made of row 1, row 2, row 3, and row 4. It's going to be a 4x4 matrix where these are each rows. And so the way that we do that is we first compute the last row, and we do that by multiplying this vector of 0, 0, 0, 1 with the inverse of our controllability matrix. And so we already had that from the previous slide in our previous activity. And so that gives us our first row that looks like this. Then we can compute the third row by multiplying our last row by a factor of A, and that gives us this vector. We could either multiply our 4, the last vector, by A squared, or we could multiply our 3 by A. So either way, whichever computation you think is easier. And that provides us with this as our second row, and then we do that one more time to get our first row. And so this makes our controllability, or our transformation matrix to controllable canonical form is given by this transformation matrix. So now we'll move on to observer canonical form. So for observer canonical form, we're going to be employing the inverse of the observability matrix, which is something we already had. Remember that in this procedure, we're actually creating the transformation matrix, but we're actually creating the inverse of the transformation matrix, and we're doing that through what we call the columns, T1, T2, T3, and T4, the columns of this inverse matrix. And so the way we did that was we multiplied the inverse of the observability matrix by this special vector, and that gives us this as our last column of the inverse transformation matrix. Then we can multiply that vector by A to get the third column. Then we can either multiply the third column by A or multiply the last column by A squared to get our second column. And then we can do similarly to get our first column. And so we stack all those into our inverse of our controllability matrix. Remember, this is the inverse. And then to calculate our actual transformation matrix, we take the inverse and get this as our transformation matrix. So now we have our transformation matrices to get to controller canonical form and observer canonical form. And so now what we're going to do is we're actually going to calculate those two canonical forms. All right, so this is the general equations of a new state variable z under a transformation where z is equal to t times x. We derived these in previous classes. So our new A matrix is going to be TA T inverse. Our new B matrix is TB, and our new C matrix is CT inverse. And so obviously you're going to need to have both T and T inverse for the controllable canonical form transformation matrix and the observer canonical form transformation matrix. So we explicitly calculated TC and we explicitly calculated T0 or TO, and so now we're going to have to calculate TO and TC inverse in order to do the rest of this calculation. So again, you can go through those calculations, just a bunch of matrix multiplications to get this as your new matrix in controllable canonical form. You can see that you've got the ones on this off diagonal, and you've got all of the other dynamical information in the first row. Again, this is in controllable canonical form, and it should look like 1, 0, 0, 0, 0. And then the rest of these are not fixed by controllable canonical form. In observer canonical form, we have ones on this upper off diagonal. All the system information is in this first column. You also have this structure for the C matrix, which is required for observer canonical form, and then this is unconstrained in observer canonical form. And notice that if you compute one, you really have computed the other. So we're doing double work to do both transformations. Notice that A0 and AC are transposes of each other. You'll notice that BC and CO are transposes of each other. And you'll notice that CC and BO are transposes of each other. So again, we're kind of doing double work here, but it just shows how both of these workflows operate. So now that we have both controllable canonical form and observer canonical form, we can go ahead and do the pole placement for the controller and pole placement for the estimator. So the first step of doing this is to write out our desired characteristic equations. And so we had poles that we wanted. They looked like -1, -2, this is -1 plus I, and this is -1 minus I. And so these are the desired pole locations, and what we do is we just multiply out these four terms to get this fourth order characteristic equation, and these coefficients are going to be what we use in order to place the poles for the controller. Likewise, for our estimator, we wanted poles. Again, since this is our estimator, we want this to be a little faster, so these are going to be -5, -6, -5 plus I, -5 minus I, and I think this should be a plus. And so we multiplied those out in order to get these characteristic equation coefficients, which are going to help us place the observer poles and eigenvalues. So now we're going to write down the characteristic equation of essentially AC plus BCK. So AC plus BCKC. So again, this is our new controllable canonical form A matrix, our controllable canonical form B matrix, and our controller gain matrix in this controllable canonical form. And we're going to do, likewise, we're going to write down AO minus LOCO, where this is the A matrix of the observer canonical form, this is the C matrix of the observer canonical form, and this is the gain matrix in the observer canonical form for the estimator. So directly from these coefficients, we can write down this characteristic equation for that AC plus BC KC matrix. And likewise, we can write down the characteristic equation for the estimator pole placement. And now equating terms, we can see that minus K1 has to be 5. We can see that 10 minus K2 has to be 10. We can see that minus K3 has to be 10, and 9 minus K4 has to be 4. And that gives us our gain matrix in the control canonical form. So this is in those z variables. In order to get it back into our x states, so we can use the x state and the x state estimate for feedback. We then do this calculation where we again take our gain matrix in controllable canonical form and multiply it by our transformation matrix into canonical form, and that gives us this as our actual gain matrix that we would use on our original system. Likewise, we're going to equate terms. We see that L has to be equal to 21. We can see 10 plus L2 has to be 166. We see L3 has to be 586. And we can see that 9 plus L4 has to be 780. And so then, again, this is in the observer canonical form. This is our estimator matrix. And then to translate that back, we have to multiply by the inverse of our observability transformation matrix to get our estimator gain matrix in our original coordinates. And so that solves the problem. You can double check these answers, or if you were working on a homework problem, you can solve this directly by using MATLAB's command called place, which uses which places the poles. And so here you give it the A and the B matrix for the controller design problem, and then you give it the poles that you want to set your closed loop system to. For the estimator design problem, for the pole placement for the estimator, you need to give it essentially this is the same command, so you need to use the transposes to say that you're going to pass in A transpose, you're going to pass in C transpose, and then give it the poles. And then that will give you the K and L matrices that achieve these poles in closed loop and should be the exact same thing that we calculated by hand in the last couple slides.